So, Chapter 7 began with a discussion on alkyl halides, and there are a variety of alternatives to alkyl halides for substitution and elimination reactions. And one of those alternatives are something that we refer to as alkyl sulfonates. And I have shown here three different types of sulfonates. So the first one is called an alkyl mesylate, and the mesylate is this part here. So this is why we abbreviate it RO. So this is the oxygen here. And then MS is for mesylate. The next one is an alkyl tosylate. So we have alkyl, and then we have the O, and then we have the TS. Okay, so TS stands for tosylate. And the last one is an alkyl triflate. So RO, and of course this is the oxygen. And then TF. TF stands for triflate. And there are other names for these. So mesylate is actually a shorthand form for methane or methyl sulfonate. Tosylate is shorthand for toluene sulfonate. And triflate is a shorthand for trifluoro methane sulfonate. Anyhow, so mesylates, tosylates, and triflates. And you might have figured out already why they are excellent leaving groups. And it's because they are the conjugate bases of strong acids. Anyhow, I'll show you that in a second. It says here they're excellent leaving groups. They're also quite large, and so we usually use these abbreviations when drawing their structure. So instead of drawing the mesylate out and the tosylate out and the triflate out, organic chemists love acronyms. We love abbreviations. So we use OMS, OTS, and OTF. So you should know what these mean when you see OMS. You should know this is a mesylate. And so on and so forth. So it says sulfonates. Why are they such good leaving groups? Well, it's because they're very stable. Like halides, they're the conjugate bases of strong acids. And here I have shown a sulfonate, and you can see the other two resonance contributors, and everybody in our class should be able to draw those kinds of resonance contributors. So the sulfonate ions are resonance stabilized. So since the anion is stabilized, it makes it a stable base, and it makes it a very good leaving group. So if you look at the pKa values, so you can see the pKa values of the conjugate acid. So the conjugate acid of a mesylate is methane sulfonic acid, which has a pKa below that of hydronium a little bit, minus 1.9. Hydronium's around minus 1.7. And then I have paratoluene sulfonic acid, so that's the conjugate acid of the tosylate, has a pKa of around negative 2.8, so about 1 log unit stronger in terms of acidity compared to the methane sulfonate, or the methane sulfonic acid. And then finally the triflic acid, or trifluoromethane sulfonic acid, so TFOH. Wowie, that's got a pK of minus 14. So you can imagine that's a really, really strong acid, and therefore triflate is going to be the best of all these in terms of its ability to be a leaving group. And if you're wondering, well, what would make that triflate or that trifluoromethane sulfonate or the triflate, why would it be so stable? It's because of the inductive effect of the fluorine atoms here, and I'm not going to go into detail about that, but you should have an idea of what I'm talking about. All right, so how do you make a sulfonate? Well, a sulfonate can be made from a corresponding alcohol. So we've seen a lot of alcohols in Chapter 7. So if I take an alcohol and I treat it with this reagent, so this is tosyl chloride, and the tosyl stands for toluene sulfonyl chloride, but tosyl is a shorthand for it. So you might recognize this here. So this, if I have just this molecule, so if I have a benzene ring with a methyl group attached to it, this is called toluene. Oops, not but toluene. Anyhow, so toluene, so this, the tosyl, what that is a shorthand form for is toluene sulfonyl. So toluene sulfonyl chloride, and I treat my alcohol with toluene sulfonyl chloride, and I treat it with pyridine at the same time. So pyridine is if I had, it's like a benzene ring, but then you have a nitrogen in the ring here. So there's a nitrogen in the ring, and I think we've seen the structure of pyridine earlier on in the class when we talked about hybridization. Anyhow, so the first step of the mechanism is going to be to perform an SN2 reaction here. So I attack the sulfur and I lose the chlorine like this, and I end up with this oxonium. And then pyridine is a base because the lone pair is basic, so it can pick up the proton from the oxonium, and I end up with an alkyl tosylate. All right, so it says here that realize that all you're doing in this case is you're just strapping or adding the TS group to the oxygen of the alcohol. So there's no change in the carbon atom bearing the hydroxyl. So what's important here is that if you take a look at this reaction here, so the abbreviations that you would use are TSCl for the toluene sulfonochloride or the tosyl chloride, right? So this molecule here, we use TSCl. And then pyridine, you're adding that simultaneously. Sometimes we abbreviate it PY. Sometimes we put PYR with a period. So pyridine, you could abbreviate it like this, whatever. Either way is fine, or you can draw the structure, that works too. But what's important is two major points of this reaction at the bottom. Number one is that you're converting the alcohol into a good leaving group, because an alcohol is a poor, or hydroxide is a poor leaving group because it's the conjugate base of a weak acid, water. Whereas when I convert it into the tosylate, I've now converted it into a good leaving group. So now I have a good leaving group. So this is a great way to take something that's a poor leaving group, an alcohol, and convert it into something that's a good leaving group. The second thing you have to realize is that I have retention of configuration. So retention of configuration. And if you're wondering, well, what does that mean? All that means is that I go from an S molecule to an S molecule. So I'm not doing the inversion of configuration, and that's very important. So to envision the compounds that can be synthesized from an alkyl tosylate, you treat them the same way you would an alkyl halide. So if you take a look at the example here, so instead of a primary alkyl halide, if I have a primary tosylate, I treat that with sodium hydroxide. Hydroxide is a strong nucleophile and it's a strong base. And again, since it's primary, I'll go back to figure 7.20, and I'm going to have mostly SN2 product. So I'm mostly going to get this product here, and I'm going to get a little bit of the E2 product. Conversely, if I have a secondary alkyl halide or a secondary tosylate, I treat it with a strong base, strong nucleophile. I'm mostly going to get the E2 product, so this would be the major product, the E2 product, and I'm going to get a little bit of the SN2 product. So again, the take-home message from this slide is you treat the alkyl tosylate the same way you would treat an alkyl halide. So no different. So that means that figure 7.20 still applies. Okay, it still applies the same way. So it says here in this question, it says predict the major and minor products for each of the following reactions. So in the first step, we're taking this chiral alcohol and we're treating it with TSCl, so that's toluene sulfonyl chloride or tosyl chloride, and then the PY stands for pyridine. So the product that you get after the first step, you remember that I'm converting the alcohol into an OTS or a tosylate, and then I get retention of configuration. That means that my dash is going to remain a dash. So I have OTS like this. In the second step, I'm treating it with potassium T-butoxide, which is a large, hindered, bulky base. And I have two kinds of beta protons. So I have the beta protons here on this methyl group, and then I also have a beta proton here. So I actually get a mixture of regioisomers. I can get this alkene from abstracting this proton, and then I could also get the more substituted alkene by abstracting this proton. So the first alkene, which is the Hoffman product, is going to be my major product, even though it's the least stable alkene, and it's because T-butoxide is a hindered base. So it's going to remove the least hindered proton preferentially. If we take a look at the next example, so let me swap out to the blue pen here. So we have a primary alcohol, so it's on a 6-membered ring. So this molecule is called 1-hexanol. So again, the first step is to treat it with the toluene sulfonochloride or tosyl chloride and pyridine. So I'm just going to draw my whole carbon chain. So let's see here, 1, 2, 3, 4, 5, 6. And then I put OTS. There's no chiral centers to be worried about. But then I'm going to treat this just like I would a primary alkyl halide. So a primary alkyl iodide or a primary alkyl bromide. So if I'm treating it with sodium ethoxide, ethoxide is a strong nucleophile, and it's also a strong base. So that means I'm going to have competition between SN2 and the E2 pathway. So what's going to happen in this reaction is if I proceed via the SN2 reaction, I'm going to get substitution of the ethoxy group. So I have 1, 2, 3, 4, 5, 6, and then I have my oxygen, and then I'm going to have my OET. So there's my ethyl, and if it undergoes elimination, so if it undergoes an elimination mechanism, I can pull off one of these protons here and make this, I can make this alkene. So in this case, since it's a primary alkyl tosylate, we can treat that just like a primary alkyl halide. I have a strong nucleophile and a strong base. So this is going to be the major product. Again, I'm referring to figure 7.20. This will be the major product, and this will be the minor product. And just to kind of get you excited about what's going on here, if you think about it, what I'm doing is I'm taking an alcohol, and I can convert it to an alkene, and there's a lot of things that we can do with an alkene, or I'm also converting it to an ether. So that's kind of interesting. It's just kind of showing you how we're moving from one functional group to another functional group. Anyhow, I hope you find this useful in studying Chapter 7.